Well, in the previous video, I left you with a bit of a bit of a clothes hanger. I left you with a bit of a cliffhanger as to what problem we wanted to look at next. Okay, so that's what happens when you're recording and your computer's battery dies. So we're picking up with a different way of looking at the first derivative test and really doing some different things with the first derivative test. So in these problems here, we were looking at the graph to make a determination on when the function has a maximum or a minimum. And the big thing about these was that this graph that we're looking at isn't the actual function, it's the derivative of the function. Okay, and so it's hard to see, but this is f prime of x. Well, in the problem that I wanted to look at next, we're looking at an equation instead of a derivative. So we're going to be given the function, and we have to take the derivative of that function and use the first derivative test to determine where is this thing increasing, and we have to determine where does it have a maximum and a minimum. So let's look at a couple of consequences of the first derivative test. If the sign changes from positive to negative, we have a maximum. Now, the sign that we're referring to is the sign of f prime. I need you to understand that when we talk about f prime, we're talking about the slope of this line. This is a tangent line. And so if we have tangent lines that look like this, or this, or this, right? Then you can see how those tangent lines would generate a curve that might look like this, right? Okay, so then we can see that if we have tangent lines that look like this and this, that's generating a curve that starts to decrease. And so there is a change from positive derivatives to negative derivatives here, and it creates that maximum. Again, we looked at some pictures of this in the previous video. If there is a change from negative to positive, we say that that's a minimum. And then if there is no change, then there is no maximum or no local maximum, no local minimum. Again, these are local max and mins, not absolute. And there was a difference, and you can go back and look at the previous videos to see those. You can look back at the extreme value theorem to see the difference there. So here's what we want to do. We're going to consider a function that's continuous, okay? So we're going to have to be able to look and tell what the domain of that function is, right? Because we're looking at some interval of the function. There are steps 1, 2, and 3 here that will walk you through what we're doing in this first problem. The other thing about this first problem is that it's the PowerPoint is really busy. Okay, so what I want to do is I want to do this problem on a clean whiteboard right here for you, and we'll take a look at how everything plays in. Now, what I'm going to do is going to look a little bit different from what you see on the PowerPoint, and I just want to give you a different perspective on this. You may like the way the PowerPoint looks. You may like the way what I do looks. I just want you to be able to have the foundation you need in order to get the problem correct. So we're looking at x to the third. Let me draw this out right quick. So we're going to have our function equal x to the third minus 9 halves x squared minus 12x minus 1. Okay? And our job is to determine the critical points and locate all extrema. So remember, extrema are those relative or local max and mins. Okay. And so we're going to use the first derivative test to do this. Now your notes indicate that the first thing you should do is find f prime. And in this problem, f prime is 3x squared minus 9x minus 12. Our problem says to find the critical points, right? So we know that if we're going to find critical points, we're going to take that derivative and set it equal to 0. Okay, so we're working through that now. And one thing I notice is that all of these values are divisible by 3. So I'm just going to divide everything by 3 to see if I can make my problem look a little more workable, I guess, is what I'm going for. We can factor this one. right? And so what I'm going to look to see is, are there numbers that will multiply to give me 4 and add or subtract to give me 3? And there are. There's two numbers, 4 and 1. The 4 needs to be negative and the 1 is positive. And so this gives us critical values that are equal to 4 and negative 1. So if I just want the critical values, or some people call them critical points, then I've got those right here. But your problem was a little more specific. It said to find the extrema, right? So it was find the local extrema. So I'm looking for a relative max. I'm also looking to see, is there a relative min? And in order to do that, we're going to use the first derivative test. So think about what the first derivative test says for just a minute, okay? The first derivative test tells us that if the derivative changes from positive to negative, we have a relative max. And if the derivative changes from negative to positive, we have a relative min. So here's how we're going to make that determination, right? Here's how we're going to do this part. First, I'm going to recognize that my function's domain, the domain of f of x, is negative infinity to positive infinity. Okay? Well, that's important to me because the next step is to take that interval from negative infinity to negative 1, and then the interval from negative 1 to 4, and then the interval from 4 to positive infinity. And let's go in and look and see what is the value of the derivative on this interval. Okay? So in other words, we're going to plug numbers from these intervals into the derivative. Now, one way to think about this is if we were to look at this on a number line, right? There are special values at negative 1 and at 4. So if you wanted to know how on earth did I create these intervals, I'm really just looking at the number line to figure out kind of what's going on. So I'm going to pick a number between negative infinity and negative 1. Let's say negative 2. Okay, and I'm going to plug that into the derivative. So the derivative, if you remember, was 3x squared minus 9x minus 12. We said that they all have a 3 in common. And if we took that 3 out, it would factor into x minus 4x plus 1. Okay, so I'm writing f prime like this because it's going to be easy on me to plug negative 2 in. Okay, so if I plug negative 2 in, I'm going to have 3 times negative 6 times negative 1. Well, this is significant because a negative times a negative is a positive. I don't care that it's positive 18. I care that it's positive. A number from this interval would be 0. So I'm going to plug 0 into this derivative. If I did that, I would have 3 times negative 4 times 1. A negative times positive is a negative. Again, it's not that I care what the actual value is. It's that I care, is the value positive or is it negative? Take a look at this one. The way I do this, I'm going to plug 5 into the derivative right here. Okay, and I'm plugging into this version of the derivative because I only care about the signs. So we could say this. It's a positive 3. And 5 minus 4 is a positive 1. And 5 plus 1 is a positive 6. So positive times positive times positive is positive. Again, I'm just doing this to reiterate to you that I don't care what the actual value is. I only care that it is positive. Now for the first derivative test. My sign was positive, now it's negative. I know that if I have a change from positive to negative, there is a relative max at x equal negative 1. And likewise, I know that if I have a change from negative to positive, then when x equals 4, we have a relative min. Okay? Now, I wanted to take you through my version of how I do the problem because it does look a little different than the version in the book or the version in the PowerPoint. Notice they list their intervals vertically like so. I listed mine horizontally. And we chose values that were similar. We chose -2, 0, and 5. It's not that there's a right or a wrong way to do that. But the next thing we did was we chose to plug the derivative into this thing here. And notice how they did plus, minus, minus, and plus, minus, plus, and plus, plus, plus. So we did something similar here, right? Now, there's a little bit of notation difference. F is increasing. I know that the function's increasing because the derivative is positive. And I know here that the function is decreasing because the derivative is negative. And then again, I know that it's increasing because the derivative is positive. When the sign switches from positive to negative, right, then we know as x increases through -1, we have a local maximum there at -1. And we said in our picture, we said at -1 we have a relative or local max. Same meaning, different words. And then we have a relative min here at x equals 4. In the PowerPoint, they go through another problem that's very similar. In this problem, though, there's something that's distinct, and it's the idea that we have an x on the bottom. So if you look, we're going to have two critical numbers. We're going to have a critical number at 0 and at 1, okay? Because the derivative is undefined at 0. So when we do our analysis, we're going to have negative infinity, sorry, that was out there. Negative infinity to 0, 0 to 1, and 1 to infinity, right? So you can see those intervals show up here. So think about numbers that are between negative infinity and 0. -1, right? Numbers that are between 0 and 1, 1/2. And numbers that are between 1 and infinity, 2. The next question becomes, where do the pluses and minuses come from? Well, if we plug -1 in up here, right, we have 1 minus a negative. Well, that's a positive value, right? And a positive value times a positive value is positive. And then on the bottom, you may be wondering why we have a positive on the bottom. Think about this. Okay? If we rewrite this, it looks like this. When I square a negative, I get a positive. Okay, so that's where that positive value comes from. In fact, I'm always going to be squaring this value, which ensures that the bottom will always be positive. Now, the big consequence is that there is a change from right there at x equal 1. So there is a local max at x equal 1. We go from positive to negative. So next steps are going to involve you going into Newton, working through those problems that you see. Remember, there are two types of problems. We're going to be looking at the derivative, okay? And when is the derivative positive and negative? And then we'll be looking at the actual functions and doing our first derivative test analysis, where we use that chart and those test points. Okay, so good luck on that assignment, and give me some feedback on what we can do to make this better, okay?